Hello everyone, my name is Felipe Frison. I am a mechanical engineering student at the Federal University of Technology of Paraná, and today we present the paper entitled Aerodynamic and Structural Analysis of a Greenhouse Made with Bamboo Cones. The authors of this paper are me and my supervisor, Dr. Diego Rosseto. First of all, let's define why you should use a greenhouse. One of the most important points is partial control of the weather conditions. This way, it is possible to produce fruits and vegetables in periods that aren't propitious, such as the winter in the south of Brazil, which is cold with frost and negative temperatures. Another important point is partial isolation against the entrance of insects that are vector of plagues. Nowadays, greenhouses are made of metal, wood or polymer materials. But then why use bamboo? Unlike metal materials and synthetic polymers, bamboo comes from a renewable source and it requires a low processing cost and can be made with simple tools. Compared to wood, it grows much faster than eucalyptus, for example, and has a high productivity per hectare. Another important aspect of bamboo is its considerable mechanical properties combined with a low specific weight. However, as bamboo is a natural material, these mechanical properties depend on many factors. Furthermore, bamboo is an orthotropic material with similar strengths in the longitudinal direction and a complexity different in the transversal direction. According to Gonçalves 2000, the properties for the species Dendrocalamus asper and Bambusa tuldoides were used, considering adult sticks without the presence of nodes within the samples in the middle of comb. The aim of this study was to analyze a greenhouse elaborated based on greenhouses for the cultivation of tomatoes and vegetables such as lettuce, cabbage, and cauliflower, very common structures in my region in the Midwest of Santa Catarina. The greenhouse has 224 square meters. For the construction of the arcs, we used Bambusa tuldoides with a 15 mm wall, while for the beams and columns, Dendrocalamus asper with 25 mm wall used. The worst enemy of a greenhouse is the wind, so it is extremely important to verify this load's action under the structure. For this, a computation of fluid dynamics analysis was performed using the CFX and the Fluent modules of the ANSYS 2021 R1 software. The considerations adopted for the analysis were Newtonian and incompressible fluid, steady state analysis, and turbulent flow. A mesh of tetrahedral elements was generated where the dimension of the first layer was found through the K-epsilon turbulence model. It's in this way the region of the interests was refined and the quality parameters such as orthogonal quality, aspect ratio, and skewness were analyzed. The quality parameters obtained were all within the limits set by ANSYS. Only the orthogonal quality was within the minimum value as below. But as there are a few elements and outside the region of the interest, with that the analysis was accepted. The potential window speed was obtained according to NBR 6123. As a convergence criteria, the RMS was used until a residue of 10 to the minus 4 was reached. A model for 0 degrees and another for 90 degrees were analyzed, obtaining the variation of external pressure. This, together with the dynamic pressure obtained by NBR 6123, was the basis for obtaining the external pressure coefficients. Looking at the flow lines, it's possible to observe that vortices are generated in the leeward side, this place where flow separation occurs. Looking at the plotting of the coefficients, it's possible to see the regions of overpressure and suction. Through data processing, the maximum and the minimum pressure coefficients for each region were obtained, which served as input for determining the wind loads. The structural analysis was done using beam elements with fixed constraints. These joints between elements were idealized as fixed, but need the study to validate this. The wind loads were defined based on the external pressure coefficients from CFD analysis and also with the internal pressure coefficients obtained by NBR 60032. For the same standard, an overload of 250 Newton per square meters was adopted. The structure self-weight was defined by material density. In the software Global Airfan, 46 load combinations were defined between ultimate limit states and the frequent and rare service limit states. With the model elaborated, a modal analysis was made for the first 6 vibration modes because according to it in 9.1 of NBR 6123, in buildings was a fundamental period of given natural frequency sets the value of 1 second. The wind loads must be calculated consider the dynamic effects due to the atmospheric turbulence. The static analysis was processed resulting in the displacement, shear force, normal force, and bending moment. Since the natural periods were below 1 second, it was accepted to calculate the dynamic pressure by the static method. Looking at the results, you can see that the structure presents a considerable displacement, especially in the arcs in the suction region, but as the bamboo presents an elastic behavior until near the fracture, and the greenhouses curve as flexible in the LDPE can be assumed a limit of 30 millimeters of deflection as the NBR 60032. The design was based in ISO 22156. Bamboo structural analysis were the structures admissible of limit states were obtained, taking into consideration bamboo quality parameters and the factors that take into account bamboo stalk croaking. With that were obtained for bending moments and shear force, axial tensile, axial compressive, axial tensile, more bending, and the axial compressive, more bending. Finally, the safety margins were obtained by relation the action and the admissible ones, respecting a critical requirement of at least 15% of safety margin, which show how for the structural elements is the front failure. With this work, it was verified that safety margins were obtained with relative comfort. However, this study doesn't stop in here, because several future studies may address the presence of diaphragms in the bamboo, variation of the cross-section and proprietors in relation to the culm, connection between the elements, and the treatment applied to the bamboo. Here are the reference used. Finally, I want to thank my supervisor who gave me the opportunity to apply a wide range of theoretical knowledge about structural analysis and the computational fluid dynamics, as well as ABMAC for giving the opportunity to show more people our work. Thank you all very much and have a great day.